Particularly, I worked on anomaly detection in industrial images, and also I provided some content for the anomaly detection bootcamp. Also, I've created a demo that I'll show you soon. Here is the outline for my presentation. First, to give you a better idea of anomaly detection on images, I'll show you a demo. Then I will talk about the MVTEC dataset. After that, I will go through 2 different methods for solving anomaly detection on industrial images. Okay, so the demo I've created is accessible publicly. So using this link, you can find it on Hugging Face. I created this based on Gradio and Hugging Face. I'm pretty sure you probably know what's Hugging Face. So I will be talking about Gradio. Gradio is a Python package that let us create simple UI for our machine learning models. To run the program, I will upload an image, and here you can see the image of a hazelnut with some defected parts on it. Our aim is to detect this part of the image that we call abnormal pixels or anomaly. Here you can see the final result. It takes just a few seconds, maybe 3 to 5 seconds to predict the model and find the defected part on the image. Let me upload another example, and we can see an image of a grid. We should choose the category of the image here, and then we can submit the image. As you can see here, our model could detect the defected part of the image. One of the most important data sets in the field of anomaly detection is MVTEC. MVTEC consists of 5,000 high-resolution images in 15 different categories with different objects and textures. Here you can see the list of the classes from MVTEC dataset. When it comes to anomaly detection, we should pay attention that during the training time, we just have access to the normal samples. And when it comes to the test time, we have some samples with defected parts. So in this picture, you can see some classes from MVTEC dataset. First row shows the normal samples. Second row shows the defected part or abnormal samples. And the third row shows the pixel level annotation for the defected part. Okay, as I mentioned, during the training time, we just have access to the normal samples. But what if to create some simulated abnormal samples using normal samples? Dream works based on such an idea. Here you can see the basic idea of the dreams. We have 3 different modules here: anomaly generation, reconstructive subnetwork, and discriminative subnetwork. To create simulated anomalies, they use a Perlin noise generator. And using the Perlin noise generator, they can capture different shapes like this. And after that, they binarize the image based on a threshold to create an image like this. Here A is the abnormal texture source that is sampled from a different data set that is completely different from the input image distribution. Finally, by mixing all these images together, we can create an image like this. We consider this one as an abnormal sample, and we will use it for the training process. Also, on the right side here, you can see some examples of simulated anomalies. Okay, I talked about the anomaly generation part. Reconstructive subnetwork works like an in-painter or denoiser. It consists of a fully convolutional encoder-decoder structure that tries to remove the artificial part from the input image. For training this subnetwork, they use SSIM loss function and L2 norm. Also, since we have created the abnormal parts artificially, we can use the position of them for localization or segmentation. Here, to increase the robustness toward our example, they use the focal loss as their loss function. And the output of the discriminative network would be the pixel level anomaly score that can be used later for image level anomaly detection. Here we can see the final result of the dream. On the left side, we have the pixel level area under ROC curve. And on the right side, we have the image level area under ROC curve. as you can see here, they couldn't get a very good result on pixel level, but they can get a very great result on image level accuracy. And here I have an image that shows the first row shows the original image that comes from the training data, and test data, there is some defected part here. We have the anomaly map overlay, this one, and we have the anomaly map, and finally we have the ground truth. Red pixels in the anomaly map image shows that abnormal part of the image, and the blue part or the blue pixel shows the normal part. As I mentioned here, they couldn't get a very good result on pixel level annotation. So this is the main reason I want to talk about this method, CFA, that consists of 3 different parts: feature extraction, patch descriptor, and memory bank. For extracting the features, they use, as you can see here, they use a pre-trained network. Here they use wide ResNet 50. And you probably know that different layers of a convolutional network have different spatial resolution. To use all the features from different layers, they first interpolate the extracted features to a fixed size, then they concatenate the features to create a patch of features. They set the patch features into a patch descriptor that is an auxiliary network with learnable parameters, which tries to convert the patch features to the target-oriented features. And in this image, we can see the memory bank. They are using the memory bank for saving the normal pictures. To reduce the space needed for saving pictures, to reduce the space needed for saving features, we just saved K features by applying a K-in on the output of the patch descriptor for the first image, and for the second image, another image. We just update our memory bank by finding the nearest neighbor and applying an exponential moving average on that. And for the training part, they use 2 different loss functions. First one is attraction loss function that tries to reduce the distance between the normal features and memorized feature. And by using the repel loss, they are trying, the samples that are far from each other are kept further away. The goal of attraction loss is to keep a certain radius between the normal samples and memorized features. Also, to compute the anomaly score, they use the minimum distance between the patch descriptor and the memorized feature. When the amount of this value is low, probably we have a normal sample or normal pixel, and when the amount of this value is high, we will have an abnormal pixel. This is the main reason I've used the CFA for the bootcamp. Among all the methods I'm using the memory bank, CFA is the fastest one. So you can see the time complexity table here. And this is the final result for CFA method. As you can see here, in both image level area under RC curve and pixel level area under RC curve, they could get a very great result. And here, there are some images that show the final output of the CFA method. As you can see here, they could find the abnormal pixels very well. And as I mentioned before, the red part shows the abnormal part, and the normal one, the normal pixel shows the blue one shows the normal pixel. Okay, I'm done. Thank you so much for your attention, and I would be more than happy to answer your question.
Hi, Masoud. Great presentation. Can you walk me through a little bit more on the generalizability of this model? And also, have you tried using other data sets outside of MVTEC?
Actually, for the second question, we are going to use some MRI-based images for the bootcamp. And the main reason I decided to use the CFA method is, first of all, it completely works on industrial level images. So other participants can use the model for their problem. Mm-hmm. And also it's fast. This is the main reason. Also, for example, for the training time, it takes just maybe 13 minutes to train the model from scratch.
Thanks, Masoud. What are the next steps for this work?
To be honest, the next step will be providing ourselves for the anomaly detection bootcamp. And also, currently, we are working on the other type of anomaly detection. For example, anomaly detection on tabular data, on graph-based models. And yeah, that's it.
Cool. Could you, just to provide some higher level context, could you explain a couple of use cases that people are coming to the bootcamp wanting to learn about?
For example, the one use case that comes from Air Canada, they have some images from different parts of an airplane, and they are trying to detect the abnormal part of the image. This is one of the use cases that comes through the industrial level images. Also, we have some use cases from the different banks. Currently, they are working on fraud detection. They are going to apply anomaly detection models on the time series or actually tabular data. But then, also, we have a use case from a company that currently are working on medical image anomaly detection. So they can use it for the aim of medical imaging. And yep, that's
very cool. Thank you.
No worries.